Alrighty, let's do this, shall we? Let's take a tour of the history of the universe. First. Passed out these slides, so there's a lot on here where, there's lots of words. Don't write them down on the slides. We got a lot to talk about. We're talking about the whole history of the universe. So here we go. So first of all, you may know that there's 4 fundamental forces that we know of in the universe. Gravity, the weak force, the electromagnetic force, and the strong nuclear force. And this is in order of their relative strength, which you could consider to be like, if you have 2 protons in a nucleus, compare the gravitational force between them to the electromagnetic, the electrical repulsion between them. Boy, is the electrical repulsion a lot stronger. We know, based on particle physics experiments, that at temperature scales, so if you convert the particles' kinetic energies into a temperature of around more than 10 to 15 Kelvin, that the electromagnetic and the weak force act like a single force. Their carrier particles become indistinguishable from one another. It's a kind of phase transition. They become what's called the electroweak force. That's the only one that theoreticians have successfully come up with a fully consistent mathematical theory for. But there's hope that the strong force and the electromagnetic and weak forces are all, if you will, different aspects of a single underlying force, which gets called, because everything has to have an acronym, the gut force, the grand unified theory force. This is a goal of, in some ways, theoretical, particle physics theoreticians, a sense that this should be the case, but the energies and temperatures are way beyond anything you can create in the laboratory. But on the other hand, the early universe was a sort of laboratory where those conditions would have held very shortly, very, very shortly after the Big Bang. Look at the time scale up there. This is time in seconds after the Big Bang, when the universe was less than 1/10 billionth of a second old. The electroweak force would have manifested itself. And then we're talking, nobody knows, but 10 to the minus 35, 10 to the minus 36 seconds. I mean, that's an unbelievably short time interval. Who knows if time even means anything on those kind of short scales. Would be when the gut force might have existed, according to estimates folks make. And then the ultimate goal would be to unify gravity with the other 3 into a super force, which also gets an acronym, a TOE. You got your gut and you got your TOE, where a TOE stands for a theory of everything, is what people call it. Certainly doesn't exist yet as a mathematical description. String theory has wanted to create such a thing, but the joke with string theory is that the big breakthrough is 5 years from now, approximately 5 years in the future, and it always will be. So, in any case, that would be around the time scale called the Planck time. 10 to the minus 43 seconds is estimated when that would have occurred, if there was indeed a moment of the Big Bang, if you will. So, with that in mind, it's sort of a backdrop for this tour of the history of the universe, if you will, starting with the Big Bang. And again, you don't have to write all this down, it's on your slides there. It's interesting that we use the word era for each of these time divisions, because era normally means in geologic time, it could be like a billion-year period or something like that. And here we've got eras. They're a tiny, tiny fraction of a second, but they're named after kind of the prevailing conditions in the universe at that time, according to what we think we know. Now, we can be confident of our physics back to the time when you'd have the electroweak force and the strong force and the gravity being separate from one another. Earlier than that, we don't have complete theories that would tell us what's going on. So that's an important caveat here. But our best understanding at this point is that we start with the Planck era. We lack a theory to describe conditions in the Planck era. That would be when all the forces were, we think, maybe, we being the theoretical particle physics type, unified into a toe. And then you get to the Planck time, about 10 to the minus 43 seconds after the Big Bang, if you will. And gravity splits off from the gut force. And so two forces are thought to have operated during the gut era, gravity and the gut force, between 10 to the minus 43 seconds after the Big Bang and 10 to the minus 38 seconds after the Big Bang. Again, it's an incredibly short period of time. Although if you look at it, right, it's a factor of 100,000. So when you get to the next boundary here, when you get the strong force splitting off from the electroweak force, the universe was 100,000 times older than it was at the time of the Planck time. It's still 10 to the minus freaking 38 seconds. It's still an unbelievably small amount of time. So, estimated, oh, by the way, the start of the gut era, estimated temperature 10 to the 32 Kelvin. Okay, now it cools down to 1,000 times cooler, only 10 to the 29th power Kelvin. The gut force split into the strong and electroweak forces, perhaps accompanied by a dramatic instant of expansion called inflation. More on that later. In the electroweak era, elementary particles appeared spontaneously from energy, but also transformed rapidly back and forth into energy. The energies are so high that you've got a soup of particles and their antiparticles. And you probably know that if a particle meets its antiparticle counterpart, then they can annihilate into a pair of photons. So there's that happening. Maybe what you don't know is that if you have photons with high enough energy, namely they've got enough to create the rest masses of the particles involved, why photons crossing paths can turn into a particle-antiparticle pair. So two very energetic photons could cross paths, and their energy could turn into an electron-positron pair. And so this would just be going on constantly. Electrons annihilating positrons, and photons making new electrons and positrons, and various quarks and their antiquarks, etc., etc., etc. It's a soupy mess, a high-energy soupy mess, until we get to the next transition, when the universe has reached the ripe old age of 10 to the minus 10 seconds, 1/10 billionth of a second, and this is when we can start being confident that we understand what's going on. In other words, we think, we basically know, but here is where our physics kind of starts to become reliable, which is remarkable if you think about it, right? In other words, we can say reliable things about the universe down to when it was 1/10 billionth of a second old, and it's fuzzy before that. Important fuzzy, we'd like to know more about that, but at 10 to the minus 10 seconds, at a chilly 10 to the 15th Kelvin, right, 10 to the 12 is a trillion, so 10 to the 15th, a quadrillion Kelvin, I'm getting cold just thinking about it, the electroweak force splits into the electromagnetic and weak forces, marking the first instant at which all four forces were distinct. So you can go a bit earlier than that when you've got the electroweak force, but boy, when you got all forces distinct at that point, when the universe is a 10 billionth of a second old, well, now we're in a situation that is obtained ever since, where you've got four separate forces. We call this the particle era, where elementary particles fill the universe, and then, at first it was so energetic that quarks and antiquarks weren't combined to make particles yet, and then quarks could combine to make protons and antiprotons, and neutrons and antineutrons, and various what we call hadrons and so forth. Still a soupy mess. So then, much, much later, so when the universe is around 10 million times, 10 to the 7, about 10 million times older than that, namely a millisecond, a thousandth of a second, right? So this is all, right? This has all happened much faster than these finger snaps so far, right? A millisecond, when the temperature is, wow, now it's like, I'm gonna go get my coat, only a trillion Kelvin at that point. We have the era of nucleosynthesis, where fusion produces helium from protons and neutrons. I don't know if there's neutrons out there. Talk more about that later. And at this border right here, So the era of nucleosynthesis, I forget exactly when they think it started. It ends about 5 minutes after the Big Bang. But at this 1 millisecond mark, protons annihilated virtually all antiprotons, but some protons remained, and that's why we're here to talk about it. So we'll say some more about that too. Okay, so you get nucleosynthesis. At this point, the chemical composition is largely set by mass at about 75% hydrogen and 25% helium. We haven't had stars yet to make heavier elements than that. There's a little bit of lithium hanging out at that point. Then we get the era of nuclei, a plasma of free electrons and hydrogen and helium nuclei-filled universe. So after the 5 minute mark, until the universe is about 380,000 years old, and the temperature has dropped to about 3,000 Kelvin. Fusion ceased, by the way, at a temperature of about 1 billion Kelvin at about the 5 minute mark. Then we get the era of atoms, which we're basically where we are today. We're in the era of atoms, so there's now atoms in the universe, and a lot of things that aren't atoms still, like in stars, you don't have discrete atoms in the interior and so forth. But we need to talk a lot about this particular boundary right here, where the universe is about 380,000 years old, and electrons combine with protons for the first time ever. And so because they were combining for the first time ever, anybody know what do we call the first time ever that protons combine with electrons? Why, that would be recombination. Yes, makes perfect sense. Recombination for the first time it ever happened. Whatever. Okay, but then, you know, we are the science where you have to stand on your head to understand the magnitude scale, right? And you have to point that way if you want to have increasing temperature on the HR diagram. So why not call the first time it ever happened recombination, right? It's all consistent. All right. First, I want to mention this business of when the universe is about a millisecond old and at a temperature of about 1 trillion Kelvin. It's the mass annihilation of baryons. So baryons are protons and neutrons, and also other 3 quark particles. But the most important ones for us are the protons and the neutrons. We are called baryonic matter because most of our mass is in our protons and neutrons, so we are named after our baryons. The mass annihilation of baryons. The universe was populated, this is a figure, by the way, from Your Cosmic Connection, which I like to use for Astronomy 260. Wonderful textbook. Very friendly read. It's meant for non-science majors, but you'll learn a lot from it. I made a chapter of it available through the study guide. Very conversational. It's a hilarious book. Anyway, the universe was populated with protons, neutrons, antiprotons, and antineutrons in almost equal numbers until the energy density became too low to make new ones whenever a pair, such as a proton and antiproton, annihilated. Not enough energy around anymore to keep remanufacturing these things. But if there was a slight asymmetry of baryons over antibaryons to begin with, then some excess baryons, protons, and neutrons would be left over after the annihilation episode. And the estimate is that for every billion antiprotons in the early universe at this time, there was 1,000,000,001 protons. For every billion neutrons, there was 1,000,000,001. For every billion antineutrons, 1,000,000,001 neutrons. So in other words, imagine you're at a big dance, and this is the worst dance ever because as soon as you grab your partner, you both just disappear in a poof of energy, right? So, okay, everybody, grab your partner. Nobody told them this. There you go, poof, 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 poof. And then the wallflower is like, where'd everybody go, right? We're made of all the wallflowers from the early universe. The protons, the neutrons, the electrons that didn't happen to find a partner to annihilate with, or maybe an anti-partner to annihilate with. So here's an illustration where the asymmetry is not nearly as large. Bunch of protons and antiprotons, p bar, neutrons and neutrons, n bar. And most of them find a partner and poof, 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 poof. I can almost hear the popcorn popping. But, oh, this proton didn't find a partner. This neutron didn't find a partner. They're left over. The rest of that stuff essentially became, as we'll talk about in a few minutes, the cosmic microwave background photons. In fact, that's how we know essentially this ratio is that there's like 1 billion cosmic microwave background photons for every baryon or so in the universe. So that's kind of an order of magnitude of the asymmetry there. And so we're made of what was left over. We're made of those leftover particles. If nature were truly perfectly symmetric between particles and antiparticles, and most reactions in, most high energy reactions that convert, that generate particles out of energy are equally good at making particles and their antiparticles. But we don't fully understand it, but there's some sort of asymmetry where the universe is just a little bit better at making particles and antiparticles. There's some sort of interactions that make particles just slightly in preference to antiparticles. If that were not the case, all the matter and antimatter in the universe would have just annihilated at this stage, and it'd be nobody around to say, wow, amazingly enough, nature is slightly asymmetric between matter and antimatter, and so a little bit of matter survived. And here we are. Yay! Yay! Thank you, asymmetry. Here we are to talk about it. Crazy. That's one of the most amazing things I've ever learned about the universe. Oh yeah, I did consider. I just wanted to talk about everything first. Okay, so now we've got the era of atoms lasted until stars and galaxies begin to form. Okay, well, let's see. Okay, fine. It's the era of atoms, and there's no stars and galaxies yet at that point. I mean, I feel like I can still say I'm in the era of atoms. There's lots of atoms around, but whatever. So, and there's some variation in terminology from one source to another, what you name all of these things. Anyway, neutral atoms formed, allowing photons to travel freely through space at the time of recombination, the first time that atoms formed from the combination of protons and electrons. Helium nuclei and electrons and so forth. So, at this point, what questions do you have? Pretty crazy that we can tell this story, right? 100 years ago we could tell this story. So that's a remarkable thing, is that we can tell what we think is a consistent story of the very early history of the universe. Wow. I like living in such an era. So let's talk about Big Bang nucleosynthesis, which gets really tiresome to say over and over again. So you say BBN, right? If you go to a cosmology conference, right, you'd be like BBN, 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 lambda CDM, BBN, BBN, lambda CDM, all sorts of things like that. So again, you don't have to write all this down. It's in the slides, and I'm going to show you what the big picture is in a few minutes after we get through all this. And for some reason, I made this one of these fancy things where things fly in like that. Okay, whatever. So, Big Bang nucleosynthesis. When the universe was less than 1 second old, a cute little baby, the temperature was greater than 10 billion Kelvin, frigid compared to earlier, but actually we probably wouldn't need a jacket at those kinds of temperatures. And protons and neutrons were turned back and forth into one another by the weak nuclear force via the reactions above. We've met these reactions before. We've mentioned how a free neutron, when it's not bound in the nucleus, it's unstable. It'll decay spontaneously into a proton and an electron and an anti-electron neutrino in order to conserve all the relevant quantities like baryon number, electric charge, right? Negative plus positive here adds up to 0, which we started with, and electron-lepton number, +1 for the electron, -1 for the antineutrino, all that stuff. Well, particles and antiparticles kind of behave algebraically in reactions. In other words, you can move an antiparticle to the other side of the reaction by replacing it with its particle. And so I can move the anti-neutrino to the other side, and I find that, well, you can also have a proton combining with an electron to make a neutron plus an electron neutrino. Or you can have a neutron combined with a positron to make a positron plus an anti-neutrino. So protons are turning into neutrons by absorbing electrons. Neutrons are turning into protons by absorbing positrons. And neutrons are just saying, I'm tired of being a neutron, and turning into protons by just spontaneously emitting particles. So it's this soupy universe where this is just going on constantly. And then we want to think about, well, what's the thermal equilibrium populations that would be occurring here? You know, I've been doing thermal stuff, so this kind of concept here. But the mass of a neutron is just a little bit greater than a proton. I should have looked up the numbers, but it's like 937 GeV versus 938 GeV. A neutron's just slightly more massive than a proton. The mass of a neutron is greater than that of a proton, so creating a neutron from a proton requires the electron or antineutrino to have enough kinetic energy to make up the difference, but creating a proton from a neutron does not require a positron or neutrino to have any KE. So in other words, if I want these two particles to make this neutron has more rest energy than they do. You need to convert some energy into mass. And so an electron that just casually walks up to a proton and says, I want to make a neutron, if they just low speed bump into one another, they can't, because that neutron has more mass than their combined mass together. And so you have to have some kinetic energy going in to turn into the extra mass of the neutron. Question, does that make sense? I'm getting at there. We need some extra energy to make that up. On the other hand, with this neutron and positron coming together, why, they can just casually bump into one another, and there's enough that they're going to make a proton here that has less mass than they do, and so you don't need any extra energy coming in. It will show up as some kinetic energy of the proton afterwards. You'd have to also consider the energy of the antineutrino, but in any case, this reaction requires input energy. They got to be moving fast enough to do it. This one does not. And that means, in other words, that it's a bit easier to make protons out of neutrons than to make neutrons out of protons. What does that mean? As a result, in equilibrium, there's always more protons than neutrons. But if the temperature is more than 1 trillion Kelvin, then most of the electrons at that temperature have more than enough kinetic energy to turn protons into neutrons. So there's nearly equal numbers of both. There's just a little bit more protons, but not much, because there's plenty of energy to go around. Everybody's got plenty of energy. It's only a slight asymmetry. But what happens to the universe as it expands? What happens to its temperature? It's decreasing because the photons are spreading out their wavelengths. That's true for relativistic particles too, because particles have wavelengths, so as the universe expands, if you've got a relativistic particle, that's measurably affecting its energy as its wavelength increases. So as the universe expands, it's cooling down. So as temperature drops in the expanding universe, protons began to significantly outnumber neutrons, because those neutrons are getting harder and harder to make because there's less and less extra energy going around with the leptons to make up that difference in mass. And fewer of the electrons and antineutrinos, in other words, had enough Ke to create neutrons. And so, when the universe was about 1 second old, at a temperature of about 10 billion Kelvin, the reactions above greatly slowed down for two reasons. One, expansion of the universe cools down neutrinos just like it does photons. You've got a wavelength, they're moving relativistically, they're cooling down. And two, it turns out that the probability of a weak interaction, which is what drives these conversions of neutrons into protons and vice versa, it turns out, wave the chicken feet, the probability of a weak interaction decreases as particle energies decrease. And so we've also got, in addition to that, photon energies are becoming too small for the creation of electron-positron pairs via that two photons cross paths and their energy turns into an electron plus a positron. If the energies of the photons combined is less than mc squared added up for the electron and the positron, there's not enough energy to make that electron and positron. As a result, all of the electrons and positrons annihilate except for the small excess of electrons, which is the ones that still exist today. So in other words, just as baryons and antibaryons annihilated one another, electrons and positrons annihilated one another as well. And that happened when, and then when that happened, when the universe was too cool to remake them anymore, you get rid of essentially all the positrons. But there's, about one out of a billion electrons didn't find a positron to annihilate and still survives today. Here's some right here. I'm pointing to some of those electrons that did not annihilate at this time. Hey, y'all, how are those electrons doing? Don't you like the fact that they didn't annihilate right after the Big Bang? Cool, right? My finger gets snapped because of some electrons that didn't find partners right after the Big Bang. So, let's continue. With I have to keep pushing button. As a result, the proton to neutron ratio froze out, it turns out, when you run the numbers, at a value of about 6 to 1 appropriate to the temperature at the time. Now I'm going to make it 7 to 1 in a few minutes. I didn't notice this little inconsistency. It's whatever. So anyway. Now there was a race against it, because the thing is that the ratio kept increasing as this process went on because more and more neutrons are dying. Anyway, now there was a race against the clock. The neutrons that decay via that neutron becomes positron plus electron plus neutron becomes, what's that key? Proton plus electron plus anti-neutrino there, anti-electron neutrino, with a half-life of about 614 seconds, about 10 minutes or so. They were not being replaced anymore. There's not enough energy to turn protons back into neutrons again, so the neutrons are disappearing. The number of neutrons was diminishing. So we had a situation of, help! Help! The neutrons are dying! Ah! The neutrons, help! We're going to save the neutrons. How are we going to do it? Why? To save the neutrons, they needed to be incorporated into stable nuclei. In nuclei that are stable, the neutrons are stable. They don't turn into protons. The simplest reaction that achieves this is the formation of deuterium via proton plus neutron becomes deuteron, deuterium nucleus, right? Proton plus neutron combined, plus a gamma ray. This doesn't tend to happen in the sun because there's not free neutrons around to do this. In the sun, two protons, remember, can combine to form a deuteron, but one of the protons has to turn into a neutron. But here in the early universe, why? There's neutrons flying around that can just directly combine with protons, and it's a fairly easy nuclear reaction because what makes it hard to fuse hydrogen into helium in stars? Why isn't it just happening in this room, right? Why aren't hydrogen atoms fusing into helium just in this room? What? Temperature's not high enough. Why do you need high temperatures?
The Coulomb barrier.
Yeah, the Coulomb barrier, right? Two protons are like, ew, get away from me, right? So they have to be moving fast enough to fuse. Well, is there a Coulomb barrier for a proton and a neutron? No, because the neutron doesn't have a net charge, and so this is easy. There's no Coulomb barrier to overcome, so this is a fairly easy reaction to make happen. Now, at higher temperatures, a deuterium thing like that would be just instantly broken apart by colliding with something else. So this won't go at very high temperatures. But if the temperature is low enough, you can make deuterons that then stick around. So as long as the temperature is more than about 1 billion Kelvin, the high energy gamma rays around had enough energy to instantly break apart any deuterium and form. But you get below 10 to the 9 Kelvin and deuterium can stick around. When the universe was about, okay, now I'm remembering when this starts. When the universe was about 3 minutes old, the temperature was about 1 billion Kelvin, deuterium was stable, and the neutrons inside were safe from decay. So we're starting to solve the problem of, help, help, the neutrons are dying. We're starting to save neutrons in deuterons. Yay, the neutrons are saved! Woo! Woo! Yeah, yeah! During the time it took to get down to this temperature, enough neutrons had decayed to increase the proton to neutron ratio to about 7 to 1. Well, this is what happens when you don't read the notes right before class. That's where I'm going to get my 7 to 1 ratio in here. Like I said, but in a minute we'll see that 7 to 1 is more appropriate for our calculation, just like I said before. Okay, so, ooh, look at this. Once deuterium was able to form, helium-4 was formed by these reactions above. So lots of reactions can produce, in the end, helium-4. Here's 2 chains that can make, or here's several chains that can make helium-4. One is this here, yeah, you make a helium-3, make a helium, all these different ways to make helium-4 that, notice, are different from the way it happens in the sun. Right? In the sun, 2 helium-3s collide, 2 protons get spat out, and you get a helium-4. But in the early universe, when there's plenty of neutrons flying around, you've got some other paths that can make a helium-4 as well. So these are like primary reactions for making helium-4. Here's the bottom line. Here's the punchline. You don't need to know all these details. I mean, you know, professionals do. You need to know these details, but, oh, it's in this. But you...
It's needed.
Okay. And it's also on Blackboard. I've got these, you can just get the presentation on Blackboard too.
There's something about getting it in the picture.
Oh, I see. Oh, okay. Okay. Got it. Okay. All right. So, here's the punchline. Almost all the neutrons ended up being incorporated into the helium-4 nuclei. That there were about 14 protons for every 2 neutrons. Yes, I know that's 7 protons for every 1 neutron, but it's more convenient to think of it like this, as we'll see. There were about 14 protons for every 2 neutrons. Whatever you do, don't find the least common denominators. Stop it. Implies that after BBN, what's BBN? The Big Bang nucleosynthesis was finished. The baryonic matter in the universe was about 75% hydrogen and 25% helium by mass. It's illustrated in the figure below. So, as a gift to you, I added to the study guide that you should be able to do this for just some arbitrary number of neutrons versus protons that I give you. It's a gift because it's easy. I just want you to understand this argument and prove it by doing it for some other proposed ratio. So, in other words, details, details, details. So if you just take it as a given that for every representative pack of 14 protons and 2 neutrons, that 2 of those protons combine with the 2 neutrons to make a helium-4 nucleus by hook or by crook, you can figure out the percentages of hydrogen and helium. So here we have, during helium synthesis, 14 protons and 2 neutrons. Why 2 of them join the neutrons to make a lovely helium-4 nucleus. And so what do you got left? Why, you got 12 hydrogens and you got 1 helium. So let's figure out the mass percentages. So what is the mass, roughly speaking, of a helium-4 nucleus compared to a proton? If a proton is, say, 1 mass unit, what's a good approximation to the mass of a helium-4? There, you can't see it, it's behind me now. What's a good approximation? 4, right, because what do we know about the mass of a neutron compared to the mass of a proton? Basically the same. There's some binding energy here, right, that has less mass than the 4 protons that would make it in the proton-proton shape. Blah, blah, blah. But it's just slow. So, to an awfully good approximation, this helium has 4 times the mass of a proton. And so when we look at what's left then, why we've got 12 mass units, if you will, in hydrogen, and 4 mass units in helium. So how much total mass are we talking from our, of course, this is all over the universe. This is a representative sample of 14 protons and 2 neutrons. How much total mass in these units is in this array right here? 16, right? Because we've got in the end 14 protons and 2 neutrons. Total mass is 16. And 12/16 of it is hydrogen. What's a fraction that, okay, now you're allowed to make, the denominator is coming up. What's another way to say 12/16? 3/4. What's another way to say 3/4 if you're a percentage person? 75%! 75%. And we've got 4/16, which of course is also 25%, or 1/4, right? Yeah. So that's the argument. Now, if you think about it, I could have said, well, what if there were 6 protons for every 2 neutrons? Just making something up. What if there were 6 for every 2? And then I could say to you, what percentage of the universe, if that had been the case, would be hydrogen versus helium by mass? Well, if it were 6 protons, right, these are gone, 6 protons, 2 of them combined with the 2 neutrons, right? So what's left in the form of hydrogen if we start with 6, and then 2 of them become part of helium nucleus, how much hydrogen is left? We have 4 protons, right, and 1 helium, and those are both equally massive, and so it's going to be, in this case, it's going to be 4/8 and 4/8, so it'll be 50-50 in that case in terms of mass, right? So, in other words, you're welcome. I'll give you a question on the exam where I say there's blah protons for every 2 neutrons during Big Bang nucleosynthesis. If that were the case, what percentage of the universe afterwards would have been by mass, hydrogen and helium? 3 points practically, right? So that's all you got to be able to do there. Because I want you to understand, this is so important that the Big Bang predicts from these calculations a composition of baryonic matter of approximately, and so what we observe, approximately 3/4 hydrogen and 1/4 helium. That's not quite right because it wasn't exactly 7-1, 14-2, but it's about right. And that was a very crucial piece of information that led cosmologists to reject the steady state hypothesis, which was that the universe has always looked like it does now, and that as space expands, some matter gets created in the space between the galaxies that eventually forms big clouds that can collapse into new galaxies. The steady state, some scientists preferred that for philosophical reasons. They didn't like the idea that the universe was a finite age. They wanted to just be that way, just have been around forever. But the steady state would not have predicted BBM, would not have predicted a hot early universe, would not have predicted this 75-25 ratio roughly of hydrogen to helium, but the Big Bang did, and that pretty much swung the pendulum over to, no, not steady state, Big Bang's a much better model. Okay. What questions do you have? Now, of course, stars are making helium today, and so the amount of helium is rising with time, but most helium is primordial. Most of the helium in the universe came from this. Only a small percentage has been made in stars since then. So the overall chemical composition of the universe was set when it was 5 minutes old. Pretty crazy. Okay? All right. So now, let's talk about recombination, right? Okay, so the early universe, before it was about 380,000 years old, was a plasma everywhere. It was too hot for atoms to form under those conditions. And so we had free electrons and nuclei, just like you have in the core of a star now, right? In the core of a star, there's no atoms anywhere because it's too hot. for electrons to combine with nuclei to make atoms. So the whole universe is hydrogen nuclei, protons, helium nuclei, helium-4 nuclei, a little bit of helium-3, because VBN made a little bit of helium-3. It made a little bit of deuterium that survived. It made a little bit of lithium. But it's mostly hydrogen nuclei, protons, helium-4 nuclei, and electrons. And it was like the inside of a star. Electron scattering made the universe essentially opaque to all wavelengths of radiation. Remember, electron scattering never met a photon it didn't like. It'll just scatter anything. So the early universe was opaque. Radiation had a Planck spectrum. It was very nearly in thermal equilibrium, and the universe was opaque. And you couldn't tell the difference because, like, there's nothing to see, right? There's no structures anywhere. But the mean free paths of photons was relatively short at that time. It was still light years, but relatively short compared to the scale of the universe as a whole. So the analogy is made is the early universe was like a fog, only it's a fog where we shouldn't even be seeing anything for two reasons. Well, actually, so okay. By terrestrial standards, that would not be a thick fog. You could see, miles and light years through it or whatever, right? So but by universe standards, it was a thick fog. On the other hand, well, you wouldn't actually see anything in it because nothing had been made yet except that soup, right? So this is just an analogy. There ain't no trees to see at this time, right? No mountains. When the universe, oh my God, they did it. When the universe recombined, it became transparent because remember that when you make when atoms are formed, right? Atoms are a lot pickier in terms of scattering radiation, right? Because atoms are like, I really would like you to have one of my spectral line wavelengths before I'm willing to interact with you. They still will, but on the other hand, the general opacity is at most wavelengths much lower when you got atoms around. So when the universe recombined, it became transparent, and the Planck radiation went its own way, right? I'm this Planck radiation in the early universe. I've been scattering around, and then the universe recombines, and all of a sudden they're like, I'm free! I'm free! And so the photons, most of them have just been free streaming through the universe ever since then. Except we sometimes obnoxiously catch them with, say, the Planck satellite or WMAP or whatever. Wow, that photon's been streaming from the time of recombination to now, and we just ate it. I kind of like that idea that I can do that, right? Ha! Gotcha, photon. But anyway, recombination was like the fog suddenly clearing, and at that point, you couldn't tell, you wouldn't have anything to see, but nevertheless, the photon mean free path had become much larger. The universe is no longer foggy. What questions do you have? This was at a temperature of around 3,000 Kelvin under those conditions. Remember that in the conditions in a star, that takes around 10,000 Kelvin. But at the densities of the early universe, we're talking like 3,000 Kelvin under those conditions. So 3,000 Kelvin, if that were a star, would it be a hot star or a cool star? It would be quite a cool star, as a matter of fact. The whole sky would have looked like this bright orange at this time. If you were, not that you could be around, nothing had formed yet, but beam me through the time machine, Scotty, to recombination. You look around, it's like, wow, everything is orange. Check this out. Everything is orange, right, is what the universe looks like at this point. So when we look further out into space, we're also looking further back in time, right? You see a galaxy that's 1 billion light years away, you're seeing it as it was about 1 billion years ago, because the universe has been expanding, and so it complicates things. But the further away you look into space, the further away you look back in time. If we look far enough, we can literally see to the time of recombination, and we do see that. From every direction in space, we are receiving microwave photons that we call the cosmic microwave background photons, the cosmic microwave background. And the existence of the cosmic microwave background, along with the prediction that helium and hydrogen would have that approximate ratio today, those were the two things that made scientists be like, you know what, there's really something to this Big Bang Theory. Because it predicts both of those things. Steady state wouldn't have predicted either one. Alternative theories didn't predict either one. The Big Bang naturally explains that there's this cosmic microwave background. Microwaves coming from every direction in space. There are microwaves now, when you look at the spectrum and get a temperature, it's about 2.7 Kelvin or so. But that's because, let's see, so back when the photons first started streaming, they were characterized by a temperature of about 3,000 Kelvin. But wait, the universe is about 1,100 times larger now than it was then. In other words, the scale factor was about 1 over 1,100 when the universe was 380,000 years old. And recombination was happening. So what about those photons? Is their wavelength the same as it was back then? No, it's about 1,100 times larger now, because that's the scale factor. The universe is, quote unquote, 1,100 times bigger now than it was back then. And remember, so it turns out that if you stretch photons all the same way because of expansion of the universe, if you start with a Planck spectrum, you end with a Planck spectrum at a lower temperature, it still keeps a Planck spectrum. So that means that the temperature of those photons, the spectrum of them today, is about 1,100 times less than it was back when they started streaming at a temperature of 3,000 Kelvin. In other words, they're at about 2.7 Kelvin now, which is, right, very cold, but the universe is bathed in the leftover radiation of the Big Bang when photons could first stream at recombination at a temperature back then, characterized the spectrum would be about 3,000 Kelvin if you look at Wien's law for the peak wavelength. Now it's 1,100 times lower because the universe is 1,100 times bigger. It's about 2.7 Kelvin. And so this is fancifully showing the idea. Here we are looking further back into space, further back. By the way, this is not to scale. The Earth is not this big compared to, 46,000 light years. I know, yes. Yeah, I should have said that, right? Yeah, I want you to understand that. One thing I want you to take away from this course is Earth is not this big compared to 46 billion light years, okay? Because this is about, the current distance is about 46 billion light years in every direction to this surface of less scattering. In other words, if we look out 46 billion light years, we see recombination. We see the era of recombination. We see photons that have been traveling that whole time, finally reaching us, where we slaughter them in order to detect them. Because that's what you do. You've got to eat a photon to detect it. We can't see any further than that because the universe was opaque back then. And so that's the furthest we can see in the universe is to the so-called surface of less scattering, about, it turns out, 46 billion light years away from us at this time. That's what we see as the cosmic microwave background. When it was first detected, we couldn't do this, but now we've got satellites and balloon-based instruments that can actually carefully map the temperature of it in different directions and see small fluctuations from one place to the next. That's what we're going to talk about after the break. But the first thing I'm going to say is, wait a minute! I'm telling you that that's 46 billion light years away, that from here to here would be like 92 or so billion light years. Wait a minute, how old is the universe?
13.8 billion years.
How much? Yeah, about 13.8 billion years. How can something be like 46 billion light years away if the universe is only 13.8 billion years old and The furthest the photon could travel in that much time would be 13.8 billion light years. How are we seeing something that's 46 billion light years away from us? Yes.
It's because of the expansion keeps getting
Exactly. Because the universe is expanding, right? That's how far away it is from us now. It's not how far away from it was when the light was emitted. It was 1,100 times closer to us than that back when the light was emitted, but the universe is 1,100 times bigger since then. That's its present distance. The expansion of the universe breaks the law. Well, stop, I don't want to say that. It doesn't break any laws of physics, but the expansion of the universe means it's not true that the furthest away you could see something is the age of the universe times the speed of light, because the universe is expanding. And so that changes it. In a static universe, the furthest you could see would be the speed of light times the age of the universe. But we're not in a static universe, says Hubble and Leavitt. We're not in a static universe, and so that's what happens there. Right? All right, great time.
Why do we say that the universe is has a way shorter lifetime?
What's that? What do
Why
you
do
say?
we say that the universe can have like 14 billion?
14 billion. So that's based on, we look at the cosmic microwave background, these fluctuations, and as we'll talk about next period, from that we can deduce the radiation content of the universe, the matter content, and the dark energy content. You can plug that back into those equations we've developed, like the Friedmann equation and the acceleration equation, and use that to run the expansion of the universe backwards and figure out how long since the Big Bang. And the answer is 13.8 billion years. Yeah. Yep. Let's do this. Let's look at what happens if you use, say, the Wilkinson microwave anisotropy probe satellite to map the tiny variations in temperature from one direction on the sky to another. The tiny variations in temperature from one region of the surface of glass scattering, 46 or so billion light years away from us, from another. And here's a figure that the WMAP science team made as an illustration, and I wish they would have chosen, first of all, centigrade? Who says centigrade? I mean, that's the same as, you do, I'm not, no. But I want to say Celsius if you're going to do that.
In Spanish, you say centígrados.
Oh, okay, so there's, okay, all right. Okay, but this is not Spanish. Yeah, so right, if we're Spanish, I can deal with it, but yeah.
In India, we do use that word a lot.
Do you? Okay, yeah, but it used to be used. Okay, never. Okay, but anyway, to summarize, just put it in freaking Kelvin. All right, but I think they did it because, well, okay, it's for the general public, right? This is supposed to be like educational. So here's Earth temperatures in June of 1992. Okay, I mean, I was fully sentient in grad school at the time, but in any case, ranging from minus 63 to 37. And even WMAP does this, of course. In reality, right, blue is hot and red is cool, but in our artistic sense, it's the other way around. The WMAP people can do that too. Hotter is red and cooler is blue, or whatever. Anyway, here's a map of the Earth with its temperature ranges and all that sort of thing. This is a projection of the sky around us. It's the same map projection that uses this for the Earth. In other words, here's the spherical Earth projected into an oval. There's a specific mathematical formula that lets you change latitudes and longitudes into coordinates inside the oval. On the sky, use a formula that changes. In this case, it's going to be galactic coordinates. So the plane of the Milky Way would be along the center of this, and this would be the so-called galactic North Pole, galactic South Pole, onto an oval like this. So this is the whole sky. They actually had to do a lot of processing to remove the effects of the Milky Way, and so force. So this is after doing processing to see just the microwave sky by itself. And the point is, oh look, temperature variations as well, but look carefully at the scale. Minus 270.4252 degrees Fahrenheit, and minus 270.4248 degrees Fahrenheit, right? That's a, for a difference of 0.0004 centigrade, but that's also 0.0004 Kelvin, because Kelvin and centigrade and Celsius, it's all the same thing in terms of the size of a degree, as it were. In other words, these fluctuations are like about a part in 100,000 or so compared to the average temperature. So the temperature of the microwave background, the CMB, cosmic microwave background, is probably the closest approximation to a perfect thermal Planck spectrum that we know of. But there are nevertheless very slight temperature variations from one location to another on that surface, and these have been called the ripples of creation, if you will, because these are sound waves in the early universe. These are sound waves traveling through the plasma that existed before recombination. And when recombination happened, they got sort of frozen in place. And as we'll now explain, we can learn all kinds of interesting things by carefully analyzing the temperature fluctuations and angular sizes of those, what we call the CMB hotspots and cool spots. Slightly hotter, slightly cooler. So far, what questions do you have? Yes?
How did they like separate out the, like is the only source of microwaves from the cosmic microwave like background?
No, and so they had to have very precise, at these kinds of temperatures, most of it is from the CMB, but cosmic dust is emitting some, so the raw map, you would see the Milky Way plane in there and stuff like that. So that had to be very carefully accounted for, and all I can say is it was done by very smart people. I don't have all the details of how they did that, but I'm confident that they were smart enough to do it. Is what it comes down to. And I'm sure Dr. Wu can tell you everything you want to know about it should you care to learn more. So, seeing spots on the last scattering surfaces from a book I wrote like 26 years ago. 27 years ago, so 1999, Charles Lineweaver in the Routledge Critical Dictionary of the New Cosmology, when this stuff was kind of just becoming exploitable, if you will. So what we're representing here is, these are sound waves in the early universe that we're talking about. The technical term is they are baryon acoustic oscillations. Acoustic meaning sound waves, baryon meaning that it's the baryonic matter, protons, neutrons, electrons kind of matter that is participating in them. Now, most of the matter of the universe is not baryonic matter. Most of it is in the form of dark matter, but the dark matter is essentially pressureless because dark matter particles, we think, you remember the acronym, we think dark matter particles, are a yet undiscovered species of elementary particle called WIMPs, weakly interacting massive particles, it's sort of like a heavy neutrino. Like neutrinos, they would only interact via a strong force, and they would only interact, oh wow, I knocked some sense into myself. It's all so clear now. They would only interact via gravity and the weak nuclear force, but they'd be more massive than neutrinos, which would cause them to not be moving relativistically. So they would be, instead of hot, like neutrinos, they would be cold, moving non-relativistically dark matter, CDM. They'd be essentially pressureless because they don't interact much with anything, including themselves. And sound waves are pressure waves, right? Sound waves happen because I squeeze some gas, the pressure rises, it makes it rebound, it expands past equilibrium, the pressure drops, the surroundings push it back together. Sound waves are driven by pressure. So the baryons and photons coupled to them would undergo these oscillations. So you'd have blobs growing, contracting, growing, contracting, growing, contracting. Whereas the dark matter would not participate. Dark matter would just start clumping together and there'd be no rebound because there's no pressure. Okay, does that sort of make sense so far? So imagine these big blobs, and I'm talking huge, much larger, right? The frequency, these are sound waves, but we're talking like, what's the frequency? Well, every few tens of thousands of years it goes through one cycle. Every 300,000 years it goes through. So these are super infrasonic, way below even elephant hearing, right? Nobody can hear something that takes thousands of years to vibrate once. So that's what we're talking about here. And so this is supposed to represent, here's a blob which is contracting and heating up as a result of that. Here's a blob which is expanding and cooling down because of that. Hence hot and cold spots. You'll have some spots which are hotter, some spots which are cooler as a result of that. And the idea is, imagine all these blobs of different sizes. So what do you think would vibrate faster? A big blob or a little blob? Or little, yeah. It's still huge, right, by our standards, but still. Would a big blob vibrate faster? Or would a little blob vibrate faster? The little blob would. Why, it's almost like if you had stars, like Cepheids of different sizes and masses. Why, the more massive ones take longer to vibrate. True of these blobs as well. Okay? So, you got this early universe blobs, right? So it's like, here's a smaller blob. Winga, 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 winga. Here's a bigger blob. Winga, winga, winga. All right? And what happens? So here's another notion. And by the way, they're also called Sakharov oscillations after the Soviet physicists who first elucidated their properties in detail. So baryon acoustic oscillations, Sakharov oscillations. So this is supposed to represent, here's time. And so this is ZEQ. It's the time, it really represents the redshift / the time when radiation and matter became equally dense with one another. And that would be the point at which the oscillations could start to occur, because when there's too much energy in radiation compared to matter, that would make it hard for these oscillations to occur. But once matter becomes dominant, when the universe was about 72,000 years old, by our current estimate, these oscillations start to happen. So here's a big blob oscillating, and at the time that it reaches maximum compression, that just happens to be recombination. And recombination stops the oscillation, because in recombination, the gas becomes transparent to photons, and pressure from the photons turns out to be crucial to driving these oscillations. So when the universe was how old in recombination? 380,000 years old, at a temperature of about 3,000 Kelvin. When that happens, the oscillations stop because the photons decouple from the baryons, and that was crucial to allowing these oscillations to occur. So if it just so happens that you're a blob with just the right size, that you reach maximum compression at recombination, you're going to show up prominently in the cosmic microwave background, because maximum compression is when you're hottest, or maximum expansion is when you're coolest. But then there's another effect of gravitational redshift, of photons climbing out of these gravitational wells. But in any case, the temperature extremes correspond to either when you're at maximum compression or maximum expansion. And if you're a blob that's just the right size, that you go through 1/4 of a full cycle, like starting out from nothing and then reaching maximum compression, that'd be 1/4 of a full cycle, because a full cycle would be maximum compression, maximum expansion, maximum compression. So start and then back again. So 1/4 of a full cycle reaching maximum compression, And then recombination happens, it's like, stop. And when we look at the cosmic microwave background, we are looking to recombination. We're seeing the oscillations when they stop. If you're a blob that was at maximum compression or maximum expansion at that moment, you will have a large temperature fluctuation relative to everything else, because that's when you get maximum compression, maximum temperature variation is when you're either fully expanded or fully compressed. Does that basically make sense? In a sound wave, right, even though we don't normally think of this, in a sound wave, the temperature is changing too, because when things compress, that does work on them from the surroundings, and they heat up, and when they expand, they cool down. So maximum density and temperature fluctuations occur when there's maximum compression or maximum expansion. If you're just the right size to get to maximum compression and then stop, recombination happens, we look today and we see an especially hot or cool spot on the sky with a characteristic size, namely the size of a blob that would have that oscillation period that would go through, reach maximum compression at that time. I'm pointing to the wrong one. I'm pointing to, this is what I meant to be pointing at. This is what I meant to do. This is one that's still compressing. This is one that just stopped compressing because it reached maximum compression at recombination. We call that the first peak because if we measure temperatures of different blobs in the CMB, the first peak is corresponding to blobs with a size such that they're the ones, the largest blobs we see that are at maximum compression or expansion. The largest blobs we see with maximal temperature fluctuations. Here, so this blob is too big. It's not done compressing by the time of recombination. We capture it somewhere in the middle of its cycle. This blob is just the right size to be at maximum compression at recombination. We capture it, we see it at maximum temperature fluctuation. Here's one that is a bit smaller. So it goes all the way to maximum compression and then starts rebounding again. Recombination happens and it's still expanding. And here's one that goes to maximum compression, and then we just happen to catch it at maximum expansion when recombination happens. And so this will also be a large temperature fluctuation because we capture it at maximum expansion. One that's a bit, just see if you're following, one that's smaller than this one, okay? So we get to maximum compression, then what's it start doing? It starts to expand, it reaches maximum expansion, and what's it start to do? It starts to compress, and we capture it when it's still in the process of compressing. So in other words, we've got all these blobs that are expanding, compressing, and the strongest temperature fluctuations will correspond to blob sizes that were just right to be caught at maximum compression or maximum expansion at the time of recombination. So I'm going to make an analogy here. There was a game show that was called Pressure Luck, and what it had, you'll see it in action here. There was this board where there was a bunch of squares, and the squares would light up. It'd be like whoop, 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 squares seeming to randomly light up, and the contestants would push a button, and whatever was lit up at the moment they pushed the button, why, they could like, oh, you get $2,000, or you get a vacation, or you get a whammy who takes away all your money. And so it's kind of like the early universe, where you got all these blobs, and then we push the button, and what do we get, right? This blob was at maximum expansion. This blob was at maximum compression. This one and this one and this one were somewhere in between. They don't have maximum temperature fluctuation. They're closer to the average. So I'll play a portion of this. There was a guy, this looks random, there was a guy who carefully studied it and discovered that it wasn't actually random, and he spent a long time memorizing all the possible patterns, and he went on the show and won hundreds of thousands of dollars, and they thought, what's going on? And they finally figured it out, and it was a big scandal, basically, but I'm like, well, you're the ones that didn't make it truly random, you know, so I got to keep the money. But anyway, here we go, it's pretty amusing.
Here we are with over 80,000 up here on the board.
It's pressure luck in the universe.
$5,000, and don't forget the whammy. And Tammy, they're both up there looking for your money. Susan and Nancy, they're not doing much looking for you, but they're looking at Tony's $950. You're in first place, Tony, you play last because of that. And the player with the least amount of money, since there's a tie between Nancy and Susan, player to our left.
Odds are oscillating. It's going to be recombination, which is the plunger.
Let's hit it.
All right, big bucks. Come on, big bucks. Come on. Stop.
Stop it over. Nancy, $0, 4 spins, but you have 3 whammies. As you know, one more
Now, the
whammy.
universe only got one spin. One
So, but you can't win the game in third place, so what's your pleasure? Here we go, all right.
Let's go, big bucks.
Stop, 4,000.
So some blobs
About $3,000.
stop at maximum pressure expansion. Some blobs, it's a whammy, they're just halfway between them, right? Et cetera, et cetera.
Our champ with 6 spins and 2 whammies. Susan, you're ready. Stop at catamaran.
Catamaran. Catamaran.
$500.
I think she gets a whammy after this, that's fine.
You have 5 spins.
What should she do?
Let's go.
How many spins does Susan have left?
What's it gonna be?
Come on, big bucks. Come on, big bucks. Stop.
Stop it on. Susan, you seem to follow suit, Renee.
All right, that's enough of that, all right? But I just wanted to go, so now, you know, I said to Miss Storms once, you know, it'd be cool, that book I told you about, Your Cosmic Connection, says, imagine a bunch of light bulbs that cycle between red and blue, where red is highest temperature, blue is coolest temperature, and they're all cycling at different rates. And you can imagine bigger ones cycle more slowly, and smaller ones cycle more rapidly. So you start them all out at like the same temperature, and then tiny density fluctuations start these oscillations, start drawing some matter in, but then that raises the pressure, they rebound, so you get these sound waves in the universe. With these light bulbs, they just all start cycling. The bigger the light bulb, the slower it cycles. And then the book says something like, you know, I forget the exact words, it's like you sing happy birthday while you're, you know, patting your tummy or something like that, and when you're done, you throw a switch and all the light bulbs just stop at that moment cycling, and you look at what color is each light bulb. And so then the idea is, well, the ones that were oscillating just such that they were either fully red or fully blue, as opposed to like green in between, those are the hot spots on the CMB that have maximum temperature fluctuations, and it's going to depend on their size. And I said to Ms. Storms, you know, I wish I had some like animation of that. And I did it before Estelle was there, because I probably have one from Estelle. But she made this animation, as a matter of fact. So they're all going to start out kind of in the middle, you know, kind of like orangish color. And it's pretty quick. But in other words, all of a sudden it's going to stop, and we'll look at, some of them will be not the right size and they're halfway in between, but there will be 3 of them that are fully red or fully blue. So check it out here. Stop! This is the so-called, I probably should, okay, so yeah, it's pretty quick. But you see what's going on there? They're cycling through, and then we capture it. Recombination is when they stop flashing, right? Notice the bigger ones are cycling slower. Boom, okay? And so we circle 3 of them. Those are the ones that have maximum temperature fluctuation. They're as blue as they can get, or they're as red as they can get. So the big blob got as blue as it could get by reaching maximum. I always have to remember if it's so the actual temperature would be based on being maximally compressed, but then there's also a redshift from the photons climbing out of the gravitational well. I forget which effect is bigger, but in any case, whatever. It's at a temperature extreme, it's at its hottest, and here's one that's about half the size, so it's cycling twice as fast, and it's at the opposite temperature extreme, because it went all the way to blue and then all the way to red. And then the third one there, 1/3 the size, vibrating 3 times faster, went all the way to blue, all the way to red, all the way to blue again. And so, in other words, the big point is special blob sizes will be the ones that have maximum temperature fluctuation. And every other size is caught somewhere in between. Does that basic idea make sense? Because there's a thing on there on the study guide about, like being able to explain how this basically works, right? Different blobs would vibrate at different periods, and recombination stops the vibrations. And so blobs that are just the right size to be caught at maximum expansion or maximum compression are the ones that show up most prominently in the CMB images from WMAP like that. Or if we continue, here's the thing. Measuring the size of these blobs, the angular size on the sky, tells us the shape of the universe. Because, remember from the last homework set where I said, imagine your little ants living on a sphere, right? Or you're living in a 2D universe, or you're, this would work on the surface of the sphere, just make the surface of the Earth. You consider some ruler at various distances away from you, and because the geodesics all converging to the pole where you're standing, being on the curved surface changes the angle that they would span compared to if you were on a flat plane, and this happens in the universe. So we got these hot and cold spots. Physicists understand the physics of these things, so you can calculate the actual physical sizes of these hot and cold spots based on the physics. It's relatively simple physics in the early universe. You got this just hot gas, et cetera, et cetera. So you could calculate how big the hot spots that reached maximum temperature variation should have been at the time of recombination. And then you can say, okay, well, given that that's 46 billion light years away, what angle on the sky would that correspond to? And so then you can compare that to what we actually observe. If the universe is flat, the hot spots will look actual size, so to speak. They will subtend an angle that would be exactly what you would predict if the light just went straight towards it through flat space all the way since the time of recombination. The answer is, from that, it turns out, the hottest hot spots should span about 1 degree on the sky today. They should be about 1 degree across on the sky today. Anybody know how big is the moon on the sky? Half a degree. So if you had microwave eyes that could see these things, the hottest hot spots and the coldest cold spots would be about twice the size of the full moon on the sky. If the universe is spherical, closed, then that makes the hot spots look bigger than they, so to speak, actually are. It makes them look bigger than actual size. It makes them look bigger than 1 degree across. And so we would expect to see them looking literally bigger. The hottest hot spots would be bigger than 1 degree. And if the universe is open, saddle-shaped, they would look smaller than that. So what we do is we look at how big are the hottest hot spots, and the answer is 1 degree, and it says the universe is flat, is what it comes down to. This is how we know from the CMB that the universe is flat from these baryon acoustic oscillations that produce these hot and cold spots in the CMB pattern. What questions do you have? This is crazy stuff, right? It's not everyday intuition, right, that we're developing here, but it works. This is the physics. Yes?
So could you explain again how exactly the hot spots would determine the shape of the universe?
So these are these acoustic waves in the early universe. And so knowing the properties of the baryon photon fluid, right? In other words, physicists can know what these are because we can sort of run the expansion of the universe backwards and infer conditions at these times. You can calculate what the oscillation periods of blobs of various sizes would be. Now what you're really doing is like making a Fourier analysis of the sound waves and looking for where the highest peaks would be in the Fourier analysis. So it's fairly fancy, but at the same time, it turns out not that hard to figure out if a blob at that time was 100,000 light years across, how long would it take to reach maximum compression? How long would it take to reach maximum expansion, that sort of thing. So we can do those calculations. We can say what physical size of a blob would be expected to be at maximum compression and therefore maximum temperature variation when the universe was 380,000 years old. Okay, so you have this thing that's that certain size, and you say, I know how far away it is. I know that surface is like 46 billion light years away from us. Well, you can calculate how big something that far away would look if it were a certain size. Just like in the homework problem. If you know DL and you know how far away it is from you on the flat surface and on the spherical surface, you did a calculation that said how big that angle, that little d phi was. And we're doing the same thing here. We're saying, what angle would one of those blobs subtend depending on the geometry of the universe? And in a flat universe where the photons are just moving through flat space-time, the answer is they'd be the biggest blobs, the biggest hot blobs would be 1 degree across, roughly speaking. And then we look at the actual pattern and we see, well, how big are the biggest hot blobs? And the answer is a degree is what it comes down to. And so that says the universe is flat. If they were bigger than that, the universe would be spherical. And if they were smaller than that, it would be hyperbolic, saddle shaped, because of the fact that the photons' paths are, if you will, distorted by the curvature of space-time in those cases. Okay. So we can be more precise about this. So I could spend 2 days on this to really, and I don't know how familiar, but how many of you have had quantum mechanics already? So you remember the spherical harmonics, the YLMs and all that business? Okay. So those are useful in more than just quantum mechanics. Do you remember from Fourier analysis that every function, okay, in this physicist sense of every, right? You can come up with pathological exceptions, but every reasonably behaved function can be written as a sum of sines and cosines. That's Fourier analysis, right? Okay? On the surface of a sphere, which is what the spherical, what the sky is, right? We're looking at this spherical surface around it. Turns out any function on the surface of the sphere can be written as a sum over spherical harmonics. You can build any function by adding spherical harmonics together with different coefficients. It's another version of like a Fourier series, except instead of sines and cosines being the so-called basis set, you use spherical harmonics instead. And remember, it's YLM in spherical harmonics. There's an L and an M, integers associated with them. And the bigger L is, the smaller scale the fluctuations from one theta phi to another are in the argument of YLM is a function of theta and phi in spherical coordinates. The bigger L is, the shorter the wavelength, so to speak, of fluctuations in the spherical harmonic. It varies more rapidly from one direction to another for larger L values. And that's what's being plotted increasing downwards on this y-axis here. And because what you can do is you can take the actual pattern from W map and decompose it into a spherical harmonic decomposition. You can write it as a sum of spherical harmonics and say, how much do spherical harmonics of each value of L contribute? And bigger blobs, which vary more slowly in angle on the sky, they vary more slowly from one place to another, they will have a stronger combination, a stronger contribution from spherical harmonics with larger L values, and smaller blobs show up as having the coefficients of spherical harmonics with smaller L values being larger. And I know, again, I could spend like at least half a period developing this fully. The basic idea is you can write the variations on the sky, those temperatures, as a sum of y00 plus y10, y11, and y1 minus 1. You may remember those are the three spherical harmonics when L is equal to 1, because M goes from minus L to L in steps of 1. And you add up y2 minus 2, y2 minus 1, y2 0, y2 1, and y2 2. Each one has coefficients, you add them all together, you write the entire distribution of temperature fluctuations on the sky as a big sum of coefficients times YLMs. And what you get is a pattern that looks like this after you square it to kind of look at the amplitude squared. How much power is there for each value of L? And the idea is that that function that you write, the L corresponding to the biggest peak corresponds to those hottest hot spots and coldest cold spots that have about a 1 degree in size angle on the sky. And then there's another peak in that function you would plot of this spherical harmonic decomposition coefficients squared, I know, that would correspond to the next peak, we would say, the next largest scale where we see spots that are significantly hotter or colder than average. So the second peak corresponds to the blobs which go through a full compression and then back out to a full expansion, or vice versa, a full expansion and then back to a full compression. Those are the ones that are roughly half the size of the first peak. They're smaller. Those also have significant temperature fluctuations associated with them. And you get this plot that shows those things. And, oops. So, okay, that was a lot. What questions do you have? You can spend quality time with me later if you want to, learn some more about this, talk some more about it. But I'm trying to get you to understand the basic idea here. Because what I want you to notice here, what this is saying is the temperature fluctuations of the largest blobs that were a local maximum in temperature fluctuation, if you will. It's bigger than the temperature fluctuations of the next largest blobs that had reached maximum compression or expansion. So the first peak is stronger than the second peak. And that means that blobs that are 1 degree on the sky have bigger temperature fluctuations than the blobs that are like half a degree on the sky, half as big. And we can also talk about how big are the temperature fluctuations for blobs that are a third of a degree on the sky, and so on and so forth, smaller and smaller blobs. Because if the hottest blobs are 1 degree across, the next grouping of hot blobs will be about half that size, and the next one about 1/3 of that size. Similar to on a string, you've got the fundamental, and then the next harmonic is half that wavelength, the next harmonic is a third of that wavelength, and so forth. It works similarly here. So the idea here is we can get important information about the sizes of the different peaks. How much bigger are the fluctuations for the biggest blobs that reach maximum variation compared to the ones that are half that size, but also had reached biggest temperature variation, but not as big as the first peak? How strong are the various peaks? How strong is the temperature variations for blobs that are half a degree across, half the size of the biggest ones, compared to those? And the answer is that it depends on how much dark matter there is in the universe. And that's the amazing thing here. how much dark matter there is in the universe compared to how much baryonic matter controls the heights of the even-numbered peaks compared to the first peak. And the idea goes like this. So if you're a blob and you are compressing, well, what's happening is dark matter is also compressing just because of gravity. Dark matter is compressing, and baryonic matter is compressing, and it's being pulled in by the gravity of the dark matter. But the blob reaches maximum compression, and the pressure is at its highest then. What's it going to do? It's no longer moving, but it's got high pressure, so what's it going to start doing? It's going to expand because it's got higher pressure than its surroundings because it's reached maximum compression. So it's going to start expanding. Now, if there were no dark matter around, it just expands. It feels its own gravity along with pressure as it's expanding, reaches a maximum expansion, falls back down again. But on the way out to maximum expansion, it's being slowed by two things. One, its own gravity, but two, the pressure is dropping. And so that's going to slow the expansion, and it's eventually going to slow down and stop before momentarily stop, before falling back down again. But what if there's dark matter there? If there's dark matter that's already compressed there, the dark matter does not rebound because the dark matter does not exert any pressure. The dark matter doesn't exert any pressure. So the dark matter only keeps collecting. It doesn't rebound because the dark matter only feels gravity, not pressure. So the gravity just keeps building up in denser regions, and it doesn't rebound because there's no pressure. But the baryonic matter gathers in the denser regions, but then rebounds because of pressure. But imagine, if there's dark matter there, how's that going to affect how far the baryonic matter rebounds? Is it going to help it rebound further, or is it going to make it not rebound as much because of its gravity? Not rebound as much. The gravity of the dark matter is working against the expansion of the baryonic matter when it's re-expanding. And so from your cosmic connection book, teamwork in the first peak. Baryons and WIMPs join forces, both gravitate. Since matter and energy tell space-time how to curve, both tend to deepen the pre-existing warp in space-time, density enhancement, enhancing the temperature contrast in the CMB on these degree-size scales. Descent and the second peak, they argue with one another. Since only baryons experience a pressure to re-expand out of the valleys, while the exotic dark matter remains in the valleys here we take to be these denser regions, the baryon re-expansion is hindered by the gravitational attraction to the dark matter. Therefore, the second peak and each following even-numbered peak shows subdued temperature contrast. Because the even-numbered peaks, if I take the first peak, maximum compression, and then the second peak, maximum compression followed by maximum expansion. The third peak, back to maximum compression. The fourth peak, back to maximum expansion. Fifth peak, sixth peak. So the even-numbered peaks are ones that compress and then re-expand, but the re-expansions are hindered by the gravity of the dark matter, which weakens their contribution to the hot and cold spots. The even-numbered peaks, the more dark matter there is, the smaller those peaks will be in this spectrum, where we look at, this is L-index harmonic, but another way to look at it is wavelength, if you will, in angle on the sky. So these are slower variations on the sky. These are faster variations on the sky from place to place. Well, you can actually, the physicists can do a theoretical calculation, and the red calculation is what we would expect if the universe is 8% atoms, baryonic matter, the white is 4% atoms, and the green is 2% atoms. And notice that, as I was saying, the more there are atoms compared to dark matter, more atoms means less dark matter for a given amount of mass in the universe, okay? notice that the second peak is taller when there's a greater proportion of atoms and a smaller proportion of dark matter, and it gets shorter and shorter the more dark matter is dominating, the more the gravity of the dark matter is dominating over the pressure from the baryonic matter. So the size of the second peak and the fourth, but it's mostly the second peak that's most important, depends on how much ordinary versus dark matter there is in the universe, baryonic versus dark matter in the universe. So here are the data from the Planck satellite, and here is a theoretical curve like those ones that I just showed you. And this is this green curve is the best fit and is based on the universe that is 68% dark energy, 27% dark matter, and 5.5% baryonic matter. That produces the best fit. So analyzing the exact pattern of those hot and dark spots, hot and cold spots on the CMB, looking at the detail of its decomposition into spherical harmonics, allows us to measure the content of the universe. I know that was a lot. What questions do you have? I want you to understand in general terms how that works. Quality office hour time is available. Right? It's the kind of thing that can maybe stand for some quality office hour time if you need it. And also that book, that chapter in that book is really nice for this. Okay, so wait a minute, what about this dark energy contribution here? The heights of the peaks tell us, the relative heights of the peaks tell us the dark matter versus baryonic matter contribution. How do we know about the dark energy? Because we observed that the fact that the tallest peak is at an angular scale of 1 to 3 says the universe is flat. And to make the universe flat, it has to be at the critical density, because all the components of the universe contribute to its geometry. And so that's where the 68% dark energy comes from. You need that much dark energy in the universe to add up to a total critical density. The overall critical density of the universe of dark matter, baryonic matter, and dark energy has to add up to the critical density, and so the 68% dark energy comes from that consideration. Okay, so cosmic inflation flattened the universe, because, okay, the universe is flat, that's kind of crazy, it turns out. So let's have Matt explain to you why it's kind of crazy that the universe is flat, except actually it's not crazy anymore. It's like what we expect. We see the universe is flat. Turns out it darn well better, which I think wasn't as fully appreciated back in the decades ago. But anyway, take it away, Matt.
Cosmic inflation describes a period of insane exponential expansion right after the instant of the Big Bang. It calls into question our very understanding of what the beginning of the universe even means. The Big Bang theory describes the earliest epochs of our universe amazingly well. There's many predictions that have been verified beyond reasonable doubt. But two significant problems with the simple model tell us that something strange must have happened in early times. An insane growth spurt that we call inflation. Today, I will explain what inflation is, why we need it, and why essentially all cosmologists believe that it really happened. The observable universe is impossibly huge, and I'm not exaggerating the situation here. It's so huge, 93 billion light years from one edge to the other, that those most distant points should never have had time to communicate with each other. And yet, at some point in the distant past, they must have been in contact. The cosmic microwave background tells us that they were once close enough together to become perfectly smoothly mixed. This smoothness of the CMB is called the horizon problem, and we talk about it in the last video. The horizon problem isn't the only troubling feature of the CMB. We can use the apparent size of the very subtle fluctuations in the CMB to measure the flatness of the fabric of the universe. of space-time? And the answer we get is very strange. Let me explain. A flat sheet of paper is flat, duh. Draw any triangle on one and add up the angles. It's always 180 degrees. Draw the same triangle on the surface of a sphere, which has what we call positive curvature, and the angles add up to more than 180. On a negative curvature, hyperbolic plane, a saddle-like structure, they add up to less. Triangles in 3D space obey exactly the same rules as on 2D surfaces, and their geometry measures the curvature of space. So now, think of those blobs in the CMB as the ends of very, very long triangles. We know the size of the brightness of those blobs. They're defined by how far sound waves could have travelled by the time the CMB was created. And we know how far away they are. They're really, really far. Using basic trigonometry, those distances tell us what the little angle at this end should be. It should be 1 degree, assuming the universe is flat. It should be larger if the universe is positively curved, smaller if negatively curved. And yes, it's pretty much exactly 1 degree. Based on the precision of our measurements so far, we know that the curvature is within 0.4 of 1% of perfect flatness. Okay, so what? The universe is flat. No, actually it's extremely weird. An expanding universe doesn't tend to stay flat, even if it starts that way. Analogy. One way to bowl a strike is to keep the ball near the centre of the alley all the way to the pins. If the ball isn't moving fast enough, then any initial deviation from dead centre will send it towards the gutter. Same with the universe. If the centre of the alley represents a flat universe, then the gutters represent extreme curvature in the positive or negative directions. If the universe starts out even a little bit not flat, then that not flatness will amplify quickly. So, if our universe is flat to within 0.4% now, then in the first instant, the universe had to be flat to 1 part in 10 to the power of 62. That's like rolling your ball really, really slowly and having it stay within 0.4% of the centre of the alley. And the alley is a light year long. Nice bowling, universe. This flatness problem is just as much of an issue as the horizon problem. Both seem strange if we assume that regular gravity was always the only force affecting the rate of expansion after the initial kick of the Big Bang. We need to throw out that assumption because it's giving us the wrong answer. That's a science thing, questioning your assumptions. Try it, it's fun. So it turns out that we can fix both of these problems with a single elegant idea called inflation. It goes like this. Start with a universe so crunched down that the entire currently observable part of it was all causally connected. Then, for a very short period of time, blow it up much faster than the speed of light so that most of it appears causally disconnected, at which point inflation stops and regular expansion takes over. This works because even a very blotchy, curvy universe is going to be much smoother and flatter on its smaller scales. Inflation takes a very tiny, smooth, flat speck of that blotchy, curvy, greater universe and blows it up to a macroscopic volume really, really fast. That inflating speck subsequently grows into the universe that we know, but retains its once subatomic smoothness and flatness. That's right, according to inflation, the universe that we see is a tiny part of a vastly larger universe that itself may well be curved. The neatness with which this inflation solves both the horizon and flatness problems really has most cosmologists thinking that something like this must have happened. For this to work, that inflationary expansion had to throw neighbouring regions of space apart at many times faster than the speed of light. It needed to increase the size of the universe by a factor of at least 10 to the power of 26 in less than 10 to the minus 32 seconds, ending when the universe was just macroscopic, something you could hold in your hand. in the subsequent 13.7 billion years since, the universe has expanded by about the same amount that it did during inflation. So what sort of mad physics could do something like that? Actually, Einstein came up with the exact mathematical description that we need, an anti-gravity term called the cosmological constant, in the field equations of his general theory of relativity. He added this as a way to allow his theory to describe a static space-time, a universe that's neither expanding nor contracting. When it was later discovered that the universe is indeed expanding, Einstein retracted his constant. But this bit of math gives us exactly the type of expansion that we need for inflation. Incidentally, it also describes the effect of dark energy, and that may not be a coincidence. The cosmological constant represents something that can happen to our space-time. Einstein is right, even when he's wrong. The cosmological constant adds some energetic stuff to empty space. It doesn't tell us what this stuff is, just that it's a property of space itself, and that it acts to drive expansion. The more space, the more of this stuff, and so the more space, the more expansion. We'll delve pretty deep into how this works in terms of general relativity in a future episode on dark energy. And we'll explore exactly what could cause such a weird sort of energetic vacuum real soon. Inflatons, scalar fields, false vacuums, all of that. For now, let's just go with the fact that empty space can propel its own expansion, and will do so if the vacuum contains a ubiquitous constant energy density. Another really important thing about the driving mechanism of inflation is that it stopped. The universe slowed down from exponential to the regular old expansion that we see today, what we call Hubble expansion. And while we know the minimum amount of inflation needed before that stopping point, we don't really know when it began, or even if it had a beginning. It may have, and there are some ideas about what got it started, but it's also possible that inflationary expansion is the default state of the greater universe. I should say multiverse at this point. This is the idea of eternal inflation. I'll get to all of these wild ideas very soon. With inflation, the Big Bang Theory takes on new meaning. When first conceived, the inflationary period was thought to have started at a particular point after the instant of the Big Bang. But once you accept inflation, there isn't necessarily a good reason to think that there was a normal expansion period before, if there even was a before inflation. In fact, the instant that inflation ended can perhaps be thought of as the moment that our universe, as we know it, came into being. In that sense, inflation is the initial kick of the Big Bang. We don't need to talk about an exploding singularity at all. Time may not have begun with the Big Bang, and so we'll rewind to before the beginning of the universe, very soon on Spade.
Fine. For what it's worth, I think that's right. I think eternal inflation is probably right. That there's this background, much larger cosmos, if you will, that's constantly inflating, and universes are little bubbles where inflation stops, and we're in one of them. That's my intuition, is that that picture is right. For what it's worth, maybe 2 cents, right? Nobody asked me. But that's my intuition, is that we live in one bubble universe in an eternally inflating background that has always been eternally inflating. So I'll give you the option. You want to watch one more cool video? Or you just like, no, I'll get out of here. What's that? 6 minutes. So can we do this? 6 minutes? Yeah, okay. So the point here is, if we look at the large-scale structure of the universe, so first of all, we think that this arose from tiny quantum fluctuations that got inflated into large-scale ripples, and the large-scale structure of the universe. This universe on the largest scales is from submicroscopic quantum fluctuations before inflation. That's one of the most amazing things I've ever heard. Here's the large-scale structure of the universe. You look, it's a redshift survey that shows what we call bubbles and voids. The large-scale structure of the universe is you've got clusters and clusters of galaxies surrounding voids that are about 100 million light years across. It's been described as like soap film, like soap suds or a sponge, where the voids are the bubbles in the soap and the galaxy clusters are the soap material itself. We need to explain this, and people have done simulations where you put in what we know about the dark matter, dark energy, and baryonic matter content of the universe, and here's the results, and this just blows me away. This is just amazing. 6 minutes, you can watch 6 minutes. It's amazing.
Since it was launched 2.5
And he has
decades
the perfect
ago,
planetarium.
the Hubble Space Telescope has become the ultimate time machine, delivering views of the universe all the way back to its early days. Hubble and other modern telescopes have aided discoveries about the evolution of galaxies, how they are arranged across the cosmos, and where they are all headed. Exactly how galaxies formed in all their different shapes and sizes remains one of the most complex problems in all astrophysics. Now, scientists have developed a way to study galaxy evolution in greater detail than ever. In a virtual universe, seeded only with the laws of physics and a set of initial conditions. This computer simulation starts just 12 million years after time zero and evolves within a volume 350 million light years across. Not everything is known, including the nature of a dominant substance known as dark matter. On the left, you can see how gravity draws dark matter into filaments, like a spider's web.
That's dark matter
On the
by
right,
itself.
gas heats up as it falls into a series of deepening gravitational webs
Dark matter
carved out
very high
by dark matter.
to make galaxies. And the dark matter
Within the
starts
volume,
concentrating
tens
in
of
those
thousands of
density
galaxies take
fluctuations
shape,
that we saw in the
mainly within the filaments of dark matter. Where these filaments meet, something strange begins to happen that will affect the character of nearly every galaxy or star. Vast bubbles of hot gas begin to form and expand outward. On the left is a closer view of galaxies that are falling into one of the central regions. On the right is the gas that envelops these galaxies. As gravity draws these galaxies together, waves of hot gas explode outward. This happens when giant black holes in their centers blast inflowing matter out in ferocious winds and jets. In time, these hot bubbles push out well beyond the central galaxies. This has the effect of limiting the amount of gas that can fall into central regions, allowing smaller galaxies to form on the periphery. It also seeds the wider universe with heavier elements created in early generations of large stars. Those elements you and I are made of. the story of our galaxy and our world. The coming together of dark and ordinary matter. That heat up as gravity compresses them. That leads to the production of metals in stars that are spread throughout the cosmos. Finally, there is light, given off by ordinary matter in a variety of wavelengths that we can record from our tiny outpost. In a galaxy, and a universe that is dynamic and complex on all scales of space and time.
Pretty cool, huh? That's your story. Keep that in mind, that's your story.
I was there, yeah, I remember it.
What's that? Oh, that's just coincidence, yeah. Yeah, that's just coincidence. It's just, we've probably seen that or something. What do we got there?
We're really looking at it.
Oh, go away, go away.